All right, everyone. We'll get started again just to make sure that we're sticking to time. So next up we have Martin van den Heuvel from Utrecht in the Netherlands, who's done a lot of really important work in understanding the hub architecture of the brain, and he's going to talk to us about hubs and centrality.
Hi, good morning. Good to be here. I hope you found coffee. Yeah, I didn't. Indeed, I'm going to talk you a little bit through on hubs. Mine isn't working as well. How is it working? It's not clicking. What did you do to make it click? I clicked it a lot. Yeah, that's...
I think they did some magic.
Can you do your magic, please? Ah, magic. All right. Okay. Well, good. So as we've heard, I think in the previous talks, that there is a growing, clearly a growing interest in modeling the brain as an integrative network. And one of the features that Sure. One of the features that the field is getting more and more interested in is actually the diversity of connectivity across the different nodes of the network. And that means that the observations that have been made is that some of the regions tend to have a 10-fold or 20-fold or 100-fold, if you will, connectivity as compared to the other nodes in the network. And this suggests actually that some elements in the network might play a bigger role in terms of the overall global structure, or perhaps communication efficiency or integration of information than others. And these so-called hubs are of general interest, not just for the healthy brain, but also in terms of pathology. And these hubs have been generally found not just in the human brain, so they're certainly not specific to human brain organization, but they've actually been found very consistently across a wide range of species, ranging to primate species that are more closely related to us in terms of evolution, but also when we look even further away from us, all the way up to actually the nervous system of the nematode, suggesting that these hubs might be actually a very fundamental way of how neural systems are organized. Even more, when we start looking at these hubs again across species, the general observation is that these hubs and their connectivity among them tend to form some sort of a central backbone in terms of communication, but also a central backbone in terms of integration of information. So that again emphasizes the importance of studying these hubs. And one way to study these central connectivity regions in the brain would be by means of graph theory, right? And that is, of course, what we're doing this morning. So in my talk, I will particularly focus on metrics to study these hubs and also to compare hubs across networks. So as a general overview, I will just go into very basic questions on what are hubs actually, how can we select hubs, once we've selected them, can we categorize them, or are there different flavors of hub, if you will? I will talk a little bit about how we can compare metrics of connectivity and metrics of hubness, if you will, across networks. And finally, if there's time, which I really do hope, is that I want to talk to you about some recent things that people have brought up when we study these networks, in particular when we compare networks across populations, and then I want to particularly discuss these things in relationship to degree and other metrics of centrality. So let's start off with a very simple one. What are hubs, right? Well, hubs, there is actually no one clear definition of hubs. So I think most of our definition is based on intuition. So when we talk about social networks, we see hubs as central players in our group of friends that are also perhaps participate in other groups of friends, and therefore they form some sort of a bridge between your friend group and some other friend group, or some social activity group, like a soccer club or a tennis club. So basically we there infer to as hubs as those ones that actually are in between. In terms of flight networks, hubs might be a little bit different, because I think here actually they facilitate some sort of a global spread of information. In a flight network, hubs are mostly those that have a very strong role in linking different cities together. So these would be the ones that actually host the most intercontinental flights. So these are two different but also a little bit related concepts of hubs. and we can both apply them to our examination of nervous systems. And one of the first observation of the importance of these hubs was actually made by Barabasi. Alex already very nicely mentioned this very influential paper in the field of network science. It's one of the, I think it's in the part of the top 100 most cited papers of all times. So that's actually how influential it is for the general community of network science. Now Barabasi showed actually he made a very simple observation. When we look at random networks, right, networks in which the edges are completely randomly distributed across our nodes, the degree distribution is a sort of a bell-shaped curve. However, many of the networks that he observed, including actually the nervous system, and in his case the nematode system, does not show this type of behavior. Instead, it actually shows a 1/f or a power law distribution function of the distribution of degree. So when we plot this on a log-log scale, it actually follows a linear curve, suggesting basically that the far majority of the nodes in the network are actually very sparsely connected. But there are just a few nodes that have many more connections than others. And this very tiny proportion actually consumes, if you will, a lot of the connectivity of the overall network, making them really influential in the overall system. Now, when we talk about the degree distribution and power law functions in nervous systems, I think the jury is not really out whether nervous system do really have a 1/f distribution. So most of the time we settle the argument by saying, well, if the degree distribution has a heavy tail or has a right tail, meaning that there are indeed some nodes that have a few fold number of connections than others, then we say there are indeed high degree nodes or highly connected hub nodes in the network. So most of the time when you're looking at your imaging data, you can search for a 1/f distribution, but we mostly settle with a heavy tail or right tail distribution. So how can we select hubs, right? What will be a good definition of a metric to select the most central, most influential nodes of a network? So let's introduce our friend here, the toy network, which is just a simple network of a few nodes and a few edges. Now, one first metric that we actually already looked at is simply counting the number of connections per node, and then simply say, well, let's select the most connected nodes of the network, and let's define these as hubs. And this is a metric we simply call degree centrality. But we can also do a little bit more advanced study of the central role of a node in the network and simply not just look at the direct connectivity of a node, but also take into account the overall structure of the network. One of the metrics to do so is to look at nodes with a short overall path length. So basically saying how well can I go from one node of my particular node to all of the other nodes in the network, and then I just take the average path length of a certain node. Now here too, there's not really a consensus, right? There's no obvious reason why one should take the average of all of the shortest path lengths of a node. In a similar way, we can also argue for example, take the maximal number of shortest paths, meaning that we say what we want is that a certain node has a minimal number of steps to reach every one of the other nodes in the network, and to take that as a metric of centrality. Another metric that is commonly used is what we call Petrina centrality. So what we do here is we compute every one of the possible shortest paths between all of the combinations of nodes, and then we count for every one of the nodes how many times this node is within a certain path between any two pair of nodes in the network. So for example, we take the green node here, it is part of this path and this path and this path, so we continuously count the number of passes for every one of the nodes, and then we take the most central nodes as those that have the highest normalized pass count. And this is a metric we call Petrina centrality. A final metric that I will discuss, although I have to say there are many others actually, and I think the field here is quite evolving, and again, there is no general consensus of what a hub would be, so if you want to introduce your own metric and you have a good rationale to do so, then I certainly encourage you to do so. But the last metric that is, I think, quite more and more often used is a metric called eigenvector centrality. It is actually a metric that is based on the graph theoretical spectrum of the graph, so it's quite complex. But a more simple definition would be to say, well, hubs are actually those nodes that have they're connected to nodes that are also important in the network. So basically what you do for every node of the network, you compute its level of influence to the overall network, and then the consensus is that those nodes that have many other nodes that are connected to many other nodes that are also important for the network, that these nodes would actually be the most to be the most influential one. And in social network, this is quite intuitive, basically saying if you have a lot of important friends, then you are very likely to be important yourself. So to recap, we can define hubs in these multiple metrics of centrality. And most of the time we just say, well, we either select hubs on the basis of their degree, or we select them on a level of the shortest path length, or the level of highest pass count between the centrality, or some other metric. But in a similar way, we can also say, well, perhaps we should select hubs just on, not just on a single metric, but actually on a combination of multiple metrics. And people are more and more doing that in that sense. And when people do that, I think there has now been quite a consensus of these hubs to be existent in nervous systems, in particular in the human brain. There was quite a lot of consensus about these central connectivity hubs to be centralized around particularly higher order association regions, both when people use diffusion MRI as well as functional connectivity. So once we have selected these hubs, are all hubs equal? Well, certainly not. Most of the time we can actually distinguish or categorize hubs in terms of their behavior in the overall network. So let's go back to our friend to toy network, but now we're going to color in the modular assignment. So again, we have the three simple modules in this network, three different colors of pink, and suddenly we can actually say that if we just take a look at both of these two highly connected hub nodes in the network, they might actually have a different behavior when we take into context these modular hub assignment. So, for example, if we take a look at the orange node, the light orange node here, half of its connections actually span two nodes within the same module, but the other two, span to both of the other modules. While in contrast, if we look at the red node, the darker orange node, all of its connections are only linked to this nodes in the same module. Right? So these all of the connections would be what we would call intramodular edges of the network. And on the basis of this different type of behavior, we tend to differentiate between so-called connector hubs, which will be nodes that are span between different modules, and so-called provincial hubs, which will be nodes hub nodes that will particularly connect to mostly nodes of the same type of modular assignment. So how can we capture these two different flavors of behavior? Well, the first metric that is introduced by Gurmir and colleagues was the participation coefficient, which simply counts the number of edges a certain node has, and in particular also the distribution of these edges across the different modules in the network. So basically what you first do, you compute the modular assignment, and then you put that into this function, and you count per node how evenly the connections are distributed across the different modules. A higher participation coefficient in that sense means that the connections of a node are more distributed across the different modules with a very low level of participation coefficient, meaning that the far majority of connections are mostly within a certain one single module of the network. In addition to this, the level of connectivity within a certain module can be strongly expressed by the within module degree z-score, which is actually indeed a z-score metric, as you can see. So basically what you do here, you take the level of connectivity of a node within its module, and you compare that to the level of connectivity within that module of the other nodes. Right? And basically if your certain node stands out on the overall distribution of the connectivity in that particular module, then you can argue that this within module degree z-score is high, so therefore this node has a strong role in the overall organization of that single particular module. And basically by combining these two metrics, one can differentiate between the connector hubs, which will be nodes with a high degree z-score, as well as a high participation coefficient, and provincial hubs would be just nodes with a high degree z-score, but actually a very low level of participation coefficient. So our fourth category that is gaining more and more interest in the community when we talk about hubs is actually the relationships of connectivity between hubs. So for example, when we go back to our toy network and we select the number of hubs, we can ask ourselves the question is, how are these hubs connected to each other? Are they like densely connected nodes but are mostly operating independently from each other? Or are they actually having a certain level of connectivity between them? Do they have some sort of a relationship together? Do they form an entity in the network as a whole. Now, one of the first features that was introduced to examine this is actually the K-core reconstruction. Now, the K-core reconstruction actually looks for the existence of a subset of nodes that within this subset has a certain level of degree K or higher. So basically what this procedure does is, if we want to examine for example, the 3 core of a network, what you do is you repetitively aim to peel off the nodes that have a degree that is lower than 3, and you do that over and over and over until you end up with a subset of nodes that actually have among them a degree of 3 and higher. So basically, in our Tor network, the remaining subset would, the 3 core would actually be this network, and as you can see, indeed, all of the nodes have at least a degree of 3. And when applied to neuroscience data, I think one of the first very nice a seminar paper in the field was the paper by Heckman and colleagues showing that the core of connectivity in the overall brain network consists of centrally connected hubs, actually quite distributed across the entire brain. Another phenomena that is related to this but is not exactly the same is the Rich Club organization of nervous systems and networks in general. So now the Rich Club actually describes the subset of nodes that are very densely connected to each other, more than you would expect purely on the degree of the individual nodes. So basically it boils down to the following question. So let's assume that we have a certain network and then we identify a certain set of high degree nodes, here indicated by the red nodes. Now the question that we can ask then is, how are these hub nodes connected to each other? Right? Would the topology of the network be in such a way that the connectivity between these hub nodes would actually be very low? Right? There would be the connectivity between those hub nodes is extremely sparse. Or would it be the case that the connectivity between these nodes is actually average in terms of the overall network, but also average in terms of the degree of the individual hub nodes? If you are highly connected, there is a certain probability that you will end up having a connection with another high degree node in the network. But this will be just random chance. Or finally, is the level of connectivity between those hub nodes more than you would expect if in terms of a chance null model? And we can very simply generalize this by a very simple formula introduced by Kalisa and colleagues, who were one of the first to report on this phenomena in all sorts of networks. Namely, simply what you're looking at is, for a continuous line of degree, you search for the level of connectivity, basically the density of the subgraph of all of the nodes in the network that have a degree k or more. So when we apply that to the brain network, what you see here is a very simple examination of this phenomena in a very simple connectome reconstruction of the human brain. On the x-axis, you see all of the different levels of degree, and then in the y-axis, you see this Rich Club coefficient. In the darker line, in the black line, you see that for every one of the level of degree, the number of connections within that subset of nodes is counted and divided by the total possible number of connections. Now, as in many networks and many metrics that we examine, we have to, of course, benchmark this again to the null model. And Petra will talk us through this, the importance of using these null models, and also selecting a good null model in the next talk. So basically what we did here is actually we take the original network, we randomize the connections, but we aim to preserve the degree sequence, basically because we want to preserve the probability of 2 high degree nodes to be connected. And if you do so, you get the dark gray, the light gray line here. And basically when we want to say there is a Rich Club organization of the network, we take the ratio between the two, and then you get the red line, arguing that if the level of connectivity between a certain subset of nodes is higher than you would expect, basically observe in the randomized null model, then this coefficient is higher than 1, and then we say there is a certain level of Rich Club organization. So this is purely math. For what does it mean in real language? Well, it simply means that actually when you go higher up in the chain of connectivity in a nervous system, then apparently there is more and more investment of resources in keeping these high degree nodes connected to each other and let them form a sort of set of highly connected, densely backbone within the overall system. And this backbone is, I think, now continuously argued to form some sort of an integration zone for different information coming from these different functional modules in the system. Okay, so how can we compare hubs across different populations? So what strategies can we have to look at differences between connectivity distribution, or degree in particular, or participation coefficient between, for example, a patient and a control population? Now, one of the ways to do that is actually the most simple way to do it. Just use any normal t-test or permutation test that you have, and simply take the nodal metrics, degree, participation coefficient, and do a t-test between your controls and patients on a node-based level. And this is actually, I think, by far still the most commonly used approach to compare controls and patients. But there are also more advanced methods introduced. A recent metric launched, I think last year by Termonen and colleagues in Frontiers basically said, well, can we also look at the global distribution of connectivity? And then can we compare benchmark basically every one of our individuals, both our controls and our patients, towards this null distribution? Or basically the distribution of normal connectivity in the brain, and then we're just going to look at, for our controls and patient populations, the level of deviation as compared to this distribution. So basically what you see here on the x-axis, you look at the left figure, what they did is they computed the normal degree distribution across different nodes of the network in a healthy control population. So you take for every one of the nodes, you take degree, you do that for, let's say, 100 controls, and then you average that, so you get a healthy distribution of degree across the different nodes of the network. And then you take every one of your individuals, both your controls and patients, and you correlate the individual degree distribution to this healthy degree distribution. And if a person would really be healthy, you would expect that it actually looks like the normal distribution of degree across the different nodes of the network, as in the healthy population. So basically, you would find a high level of correlation coefficient. Now, if in a patient condition, if this certain type of disease, let's say schizophrenia or Alzheimer, affects the connectivity of the system and also affects actually the distribution of degree across the different nodes, you would find a correlation that is basically a distribution that is differentiating, right, deviating from this healthy control population. So basically, when you take the correlation coefficient between your individual patient and the disease the control population, you will get a correlation coefficient that is lower. So now you get, for every one of the controls in the patients, you get a correlation to the normal healthy distribution. And then, of course, again, you can do a t-test or permutation test in between those metrics, giving you an information on how the overall degree distribution is different. And when people have looked at hubs in terms of neuropathology across different disorders, most generally people started to notice that hubs tend to not be affected in one single disorder, but they seem to be actually affected across a wide range of disorders, if not all. A very nice study, if you're interested in this, in studying hubs in general, but perhaps also studying hubs in disease, is a paper by Crossley and colleagues in collaboration with Ed Bulmer's group in Cambridge, in which they did a very large meta-study. So they used a large database on VBM results, and what they found is that when you look across a wide range of brain disorders, ranging from autism to ADHD to schizophrenia to bipolar disorder to Alzheimer and to other types of neurological disorders, is that most often there are deviating patterns found in atrophy metrics, particularly in nodes with a higher degree, suggesting that perhaps hubs might be generally vulnerable to any types of disease process. So in the rest of my talk, I want to discuss a couple of things that I think gain more and more interest in the field on when we study networks in general, but also particular in this case when we want to study hubs. And the first thing was noted actually a couple of years back in 2013 already by a very nice paper by Jonathan Power and colleagues in Neuron, in which they noticed that actually the community structure and the selection of hubs, in particular in functional networks, tend to strongly co-vary. Actually, to some extent, that it might actually be biased, giving you a bias when you select hubs in terms of functional degree. So what he noticed is that if you take simply the community structure of the network, that hubs are more often found in those communities that are bigger. And there's actually quite a simple explanation for this. So let's go back to our toy network. And the argumentation here is that the community size is an important driver for functional connectivity degree. So when we have our original toy network, right, we have to realize that this toy network is actually the result of a long range of processing steps, including, to some extent, particularly in this case, some sort of a thresholding step. So, and most of the time, the nodes that are in the same community, these nodes tend to be more spatially close to each other, or more generally, they tend to have a higher level of connectivity between them. And the reason for this is actually, well, that's the reason why they ended up into the same module, right? However, the long-range connections, these will be the connections that are more likely to be pruned off by a thresholding algorithm. Most of the time, these have a low level of functional connectivity because these are nodes that are participating in two functional modules. So over time, there is very likely that their correlation will be lower, right? Their activity will be not as synchronized as two nodes that are participating in the same functional module. Now, if you have a module that is larger, that contains more and more nodes, then if you have a node within that module, it's very likely that it will be connected. That's actually the character of the correlation coefficient to most of the other nodes in the particular module. So put differently, there is a high chance of getting a high K in a module that is larger compared to if a module is smaller, it contains only a few nodes, and it's almost impossible to get a super high degree in that particular module. So then if we take this toy network and we do hub selection, we will get a certain level of bias to finding particularly high degree nodes in the module with the largest N. And this is actually argued by the Power paper to be one of the driving factors of why, for example, the full mode networks tend to be somewhat overrepresented, if you will, in terms of functional degree. And they argue that perhaps we should use more advanced metrics to look at the centrality. And then if you do that, you will find actually a more distributed level of connectivity and of hubs in particular across the different functional systems of the brain. They also noted that this effect tends to be the strongest for correlation-based metrics. So when we talk about functional connectivity or networks that we define on basis of morphological properties, covariation networks, while the effect is less strong when we, for example, look at anatomical networks in which connections are actually defined based on diffusion MRI or neuron-to-neuron reconstructions. So the second topic that I think that is important, the second thing that has gained more and more, I think, interested in recent literature is the influence of false positives and false negatives on network configurations, and in particular, I will focus here on degree. A very nice paper that I argue and encourage you all to start reading this is a recent paper by Andrew last year on basically the question of which one should we go for, sensitivity or specificity. And in particular, Alex already mentioned this, there is a trade-off, right? We can't always have all. Sometimes we have to make a decision and we have to choose whether we go for sensitivity or specificity in terms of reconstruction methodology. In particular, what I think this paper mentioned is that actually when we include a potential false positive in the network, this has a more devastating effect on changing our network topology than actually forgetting about a connection that is actually there, namely a false negative. And this is not always, I think, very intuitive. In most cases, when we study certain systems, we argue that the inclusion of a false positive and false negative is even, so we have to go a little bit in the middle, so take a few hits on the false positive, but also take a few hits on the false negative, so we can trade off a little bit between sensitivity and specificity. And as a Dutchman, we like to polder, so we would like to have this balance, but in networks that might not always be the case. And this year, Andrew and I teamed up and said, what is this effect actually when we start to do control-patient comparison? Because if it is the case that a false positive has a more devastating effect on your network topology, then if you ended up in some sort of a situation in which your control or either your patient population has a higher bias of including a few more false positives, as compared to the other groups, this might have a devastating effect on your overall network topology and the metrics that you compute. And basically, the argumentation here is the following, that if you have a network that has a generally low level of functional connectivity, which is in most of the cases your patient population, then you're just a little bit more likely to include a false positive. Now, if you include one or two more false positives, this will have a strong effect on your network organization, more than when you include a few false negatives. So basically what you end up with is a slightly little bit more random network organization in networks that are based on low functional connectivity. Simply because low functional connectivity edges are a little bit more prone towards a little bit more bias and noise. Now here comes the trick when we start looking at degree and hub selection. So random networks, as we've seen in the Barabasi paper, they have a different degree distribution. Right? These are the distributions that are a little bit more, are less skewed, and they are a little bit more bell-shaped, if you will, compared to the ones that we've seen in the skill-free organization. So this might lead, if you will, to individual differences in hub distribution. Right? Remember, if our patients are based on lower functional connectivity networks, they might have, on average, a little bit more false positives, so their end result, their networks might look a little bit more random. So in the end, also the degree distribution will look a little bit more to the random situation. So to finalize this argument, if low functional connectivity networks are more present in patients, the network, but also the hubs in that network will be more randomly distributed. So when we go back to more advanced metrics that have been introduced in the field, we have to take into account and we have to start figuring out how we can correct for this effect when we, for example, compare our hub distribution in the controls versus our patients. And certainly we don't have an answer to this. We don't know how one should correct. So basically, for the sake of argument, what we're doing now is most of the time we're just removing some of the subjects from our populations to make sure that the level of functional connectivity is even between the two groups. And some of us have at least suggested some permutation methodology to actually keep track of the level of difference between functional connectivity between your patient and pseudo-random control and patient population. So these might be some solutions to the problem, but certainly we're not there yet. But it is at least something to take into account when you do this type of analysis and when you look at hub distribution, in particular when you compare controls and patients, then take into account this difference in level of functional connectivity and how this might influence your end result. A final remark, I think that is important when one does examine hub connectivity and want to select hubs, and also to want to compare hubs across patient populations. Should we go for a high resolution atlas? Should we aim to split the brain into as many nodes as we can and then reconstruct the network on a higher resolution, or should we go for the more lower resolution? Alex already mentioned this, and I think also in terms of hub connectivity, this could be an important factor. Because here, again, it is a certain trade-off, right? If we go for the higher resolution, sometimes we might actually need that to find nodes that have many more connections than others, right? If the network is really small, it's really difficult to find nodes that have a 10-fold or 100-fold more connectivity than other nodes in the network. So for that extent, if we really want to look at a 1/f or skill-free distribution of networks, we need to go to the higher resolution networks. And some of us actually try to go to the voxel resolution. However, there is certainly no free lunch here. There is a certain price to this, namely that if we again go to the higher resolution, we will include more noise. So in that extent, actually going to the lower resolution might bring us more reliable hubs. So here too, keep track of the methodology that you use, in particular in relationship to the question that you want to answer in terms of hub organization and hub differences between your controls and patient population. So to conclude, I hope I convinced you that hubs are quite important to examine and that they might form another metric that could be of interest when you study your patient control population. There are several metrics of centrality out there. Most of them are part of, for example, the brain connectivity toolbox. And there's no overall consensus of what a hub is, and that there's actually quite some flexibility on how you would define a hub. And this, again, pretty much relates, I think, to the specific question that you have in your study. We can finally, once we have hubs, not all hubs are equal. We have vanilla and we have strawberry ice cream, basically. We can categorize them into these different types of roles in the overall network. And finally, hubs tend to be most centrally connected elements of the network, and this might also make them vulnerable to several different neuropathological conditions. Finally, I'm going to, just like Alex and Andrew plugging their book, I'm going to end with a shameless plug on a workshop that we every year organize at summer school, which is a week of intense boot camp on connectomics. So if you're interested, just go to our website. I think for this year we have 2 or 3 seats left. So if you're interested, then give us a call. Thank you very much.